Hi guys, this video will be on implicit differentiation. Right, we use implicit differentiation when we encounter with a function that consists of several terms in one side. Right, for example, such as this, you have x and y both in one side, right? The one that the kind of differentiation that we have done up until now is now we have one function that is in one term. So for example, y in terms of x, x in terms of u. So we have already we have one variable in one side and another variable on the other side. So that kind of arrangement in your functions, we can use the derivative that have been discussed before. As for this one, this kind of functions where you have mix of terms in one side, left hand side and right hand side, the best way is to use implicit differentiation. Right, we can still use the ordinary differentiation way, which is by using by rearranging this function in one terms. For example, we can always make instead of 25x squared plus y squared equal to 109, we can always sort it out, right? Rearrange these functions of y in terms of x, so we can make y equal to 109 minus 25x squared. Okay, we're going to see that later. So if you look at this, they are using implicit differentiation and they get this answer, negative 25x over y. Let's try to do that. Let's try to rearrange this and use the ordinary way of differentiation to see whether we can have the same answer or not. Right, so by rearranging this function, right, for to become y equal in terms of x, so this is what you get, y equal to 109 minus 25x squared. Okay, so now that we have changed it in this form, we can try to differentiate it, not using implicit differentiation, but just the ordinary way of differentiation. Alright, so just to make things easy, as I said before, we change cert into 1 over 2. And of course, in this form, you can try to differentiate it using chain rule, or maybe just alternatively use the product rule with additional differentiation as we discussed in the previous video. So that's what I did here. Okay, right, after we try we multiply this constant with this is what you should get. Okay, this is the final answer, and now let's compare it with the solution given by this question. So you have the final answer as negative 25x over y. At first, right, you'll see that that is not the same, but let's try to rearrange it again. We have negative 1 over 2 here, meaning that this can be changed into a denominator, right? And 1 over 2, let's change it back to cert. Okay, and this is the next form that we can have, right? The alternative form for this one. Now it is still not the same, but please note that this is y, as we have already know that y is equal to this. So if we try to substitute it, we'll get 25x over y, which is the same as this. Okay, so basically we can do that, but unfortunately in some situation where you have a mix-up of functions that is quite complex, right? It might be inefficient to rearrange it all the time, right? You might also dealt with not just square, might be cube, might be a higher power. So instead of using this way, where you need to rearrange it to solve it using dy dx, we solve it using implicit differentiation. Okay, now let's see. Let's try to discuss exercise 4.9 here, to see on how to conduct implicit differentiation. Let us start with this question, right, which is, seems a little bit more appropriate for us to discuss implicit differentiation as a whole. Okay, so the first step, right, in conducting differentiation, the proper step is to put a notation of differentiation to all of them, which is d over dx, because we don't have we don't really have dy over dx, because we are just going to differentiate all of them. Okay, so this is how you write it down: d over dx for this one, plus d over dx for this one, plus d over dx for this one, and this one, and this one. Okay, so basically what these equations tell you is that you will need to differentiate each of them, right? You're going to differentiate each of them. So 1, 2, 3, 4, 5, right? You need to differentiate it 5 times. So how you differentiate it, right? We'll go back to the basic idea of differentiation, right? To the basic rule of differentiation. You need to see one by one. So for this one, you have x times y to the power of 3. So to differentiate this, you are going to use product rule, right? And also a bit of power rule. And for this one, you have product rule with power rule. Okay, and this one is just a constant and constant. So you are going to need to use all of the information that we have later. You are going also to see that we are going to use a little bit of chain rule in this. So let's try to do that one by one. Let's start with this one. Okay, let's look this side, right? So this is, as we discussed before, a product rule, right? So a product rule calls for this formula, right? U v prime plus v u prime. And just so that we are all clear that u prime here is equal to the derivative of du over dx, right? We are taking dx, right? And the same goes for v prime, dv over dx. So let's define them. So we have x, u equal to x, v equal to y3. So the u prime, or du over dx, is 1, right? We have u in terms of x, so just differentiate it 1. As for v prime, we have a little bit of problem because it is dv over dx. So we expect to differentiate v in terms of x. But now we don't have dv over dx, we have v and y. So this is what this is a situation where we need to use a little bit of chain rule idea, where we can bridge the v and the y to become dv dx through the formula of chain rule. So dv over dy times dy over dx. So we do have dv over dy, right? We can find the derivative of dv over dy because this is the function that can be used to find dv over dy. So dv over dy later will give us 3y squared times with dy over dx. So we don't have that information. So this is what we do. We just write it back, right? Sorry, so this is 2. Right, so we just write it back. So 3y squared times dy over dx. Okay, so now that we have all of this, u, v, u prime, v prime, the next thing is um, to rearrange it in this formula. Alright, so u times with v prime plus with v times with u prime, and tidy up a bit, and this is what you get. So this is the last result for our first derivative. Okay, let's put it there. So plus with the second derivative, let's do this one. As you can see, there is still a product rule, so this will apply. And we are going to use the same idea as we did before. So we have ux squared, vy squared, the u prime, which is du over dx is 2x. As for v prime, we don't have dv over dx, so we are going to apply a bit of chain rule in it. So dv over dy times dy over dx. So dv over dy, yeah, we can use this one. So it will become 2y, and dy over dx, right? You just copy it back because you don't have y to in terms of x. So 2y times dy over dx, and we input it in this formula, u v prime, so x squared times with v prime 2y dy dx, plus with v u prime, so y squared times with u prime to x. So tidy up a bit, and this is what you get. So let's input it in our equation. And the next one is this. So what is the derivative of 3x squared? So this is direct, right? So we just differentiate it. We get 6x. And then for this one, this is constant, so you will get 0. So, and this is also 0. So equal to, this is, we eliminate it. And then for this one, this is also equal to 0. So 0. 0. The next things to do after we have differentiated all of them is to rearrange them. Right? Rearrange it again. So those with dy and dx will be one side, and those without dy and dx will be on the other side. Right? So after we arrange it like this, we can later factorize dy dx out. Right? So this is what you get. And lastly, we can bring this function to the right hand side to give us the answer of dy dx. So this is the answer, right? The result of our implicit differentiation. Okay, so that is on implicit differentiation. Okay, as you can see, implicit differentiation can be a little bit complex, but if it is actually because of the differentiation that need to be done, right, in each of the function inside. Right? If you can break it down one by one like this, you just put, you can do it one by one and pull it back in our equation. It will be, it is actually not that complex. Okay, so thank you.